All right, welcome everyone. Thanks for joining the webinar. Today we're taking a closer look at Helion, a new Python embedded DSL that makes writing high-performance machine learning kernels easier. First, I'd like to introduce the speakers, Jason Ansel, Oz Wogan, and Will Fang, who are the core developers of Helion. And my name is Jung-Suk Choi, the engineer manager for the project. Today, we'll cover some of the latest features that we have been working on, as well as share the best practices for developing, debugging, and deploying Helion kernels. Please ask questions along the way. We'd like to make this as interactive as possible. So what is Helion? As I just mentioned, it is a Python embedded DSL for writing performant and portable machine learning kernels. It compiles down to Triton, and we are also developing other backends, some of which we will cover today in the webinar. With PyTorch native syntax, Helion raises the design abstraction to make kernel authoring dramatically easier. And our Autotuner explores thousands of configs to find the most performant implementation. Helion was just launched in beta at PTC 2025. All right, with that, I'll hand it off to Oz, who will talk about the latest features and backends that he has been working on. Take it away, Oz.
Yeah, thank you, James. So for the most part, during the James introduction, we talked about portability. And one of the main goals for Helion has been hardware heterogeneity. And currently, Helion supports multiple hardwares via the Triton backend, as we just mentioned. We started off with our most commonly used backends like NVIDIA and AMD GPUs, specifically the industrial versions where like A100, H100, B200, and the next generations. And the same goes for AMD with like the MI 300X and like the 350, 400, etc. And then later, we recently added Triton CPU support so that we can run on the CPU. And since our backend is Triton, we can also run on accelerators that can consume Triton. An example of this would be Meta's internal accelerator, MTIA, as publicly discussed. So one of the interesting things here is that right now we're only supporting backends using Triton. And we would like to actually go to more, we would like to increase our portability and explore newer backends so that we can support more hardwares. Sorry. So the reason why we started off with Triton was we wanted to first target the most popular industrial GPUs, and Torch Inductor already has a Triton backend. And maybe this would be a good time to talk about how Helion consumes how a Helion and Torch Inductor interacts. As we discussed in the past, during our presentation, the way Helion works is that Helion, actually, let me get there first. Okay, so we discussed this figure before. Essentially, the way Helion works is that we have our own code type propagation system, which parses through the Python AST and then adds extended types. And then we do some analysis to generate our device and our host IRs. And then once we have the IRs, we do the code gen. For code gen, we have FX operations and ATON operations, and we didn't want to re-implement all the hard work that Torch Inductor does when it does the conversion from these FX ATON operations into Triton output code. So we are taking advantage of the existing Inductor's ability to code gen kernels for these operations. And that's why we started off as the Triton being our first backend. So the interesting aspect of this is that if there's already an existing Torch Inductor backend for a particular hardware, then we can actually take advantage of that and have Helion generate code. I said this is technically because it's not as straightforward as this. It actually requires a bit more work. Once there's a Torch Inductor backend, we can have Helion start consuming that. But this means that we also need to update our custom lowerings. We need to add tuning knobs. So an example of this would be currently, like for NVIDIA hardware, we have the warp specialization, or we have the reduction DIMMs. These are more NVIDIA-specific optimizations. So if we wanted a different backend, we would have to have new knobs specifically for that backend. And we're going to go into this a little bit later in the presentation. And for custom lowerings, sometimes these hardware have their own custom functions that do some ATON operations. And more specifically for Helion, we don't really support the entire set of A10 operations, but rather we have our own custom A10 operations because we support additional operations on top of the regular set of A10. An example to this would be control flow. In regular A10, there's only there's specific cond operations, or there's specific while operations. Whereas for Helion, we wanted to support a larger set of Python language. So we implemented our own conditionals, we implemented our own looping mechanism. So we have some custom lowerings that help us use these backends in these cases. So continuing on, so the first new backend we would like to introduce is Helion emitting Pallas and Mosaic kernels for various backends like CPU, GPU, and TPU. Recently, both the TPUs have been more popular, and it's an area that we would like to explore more with Helion. So we're building a new torch inductor backend for emitting Pallas and Mosaic. The way we're going to do this, and this is already a work in progress, but Helion actually emitting these will still take some time. The way we're doing this is that for CPU, we're going to be using interpreted Pallas. For GPU, we're going to emit Pallas via Mosaic, and same goes for TPU. The way we're thinking about approaching this is torch inductor will have the capability to emit a Pallas kernel for your specific hardware, and then we're gonna have Helion tie into the exact same mechanism we did for Triton to actually emit these Pallas kernels, and then we're gonna introduce new tuning knobs specifically for Pallas operations, and this will help us emit a performant code for TPU. So the goal here is that you will still write your exact same kernel you've written for any other hardware. Like say that you wrote one Helion kernel for an NVIDIA B200 machine, assuming that this kernel does not use any hardware-specific features like inline Triton or inline PTX, assuming meaning that you stay with the regular set of operations for Helion kernels, we will be able to easily port this kernel to a TPU for you without you doing anything. And then our Autotuner will go through our new configuration, and then we'll be able to identify what's the most performant set of configs for this kernel to run on a TPU. So this is a new area that we've been exploring. Let's take a look at an example. So note that these are still note that this entire backend is still a work in progress. So this will likely take us some time to make it fully functional and have the most performance. But we wanted to give an early preview today. So let's say that you have your input PyTorch code is a torch.sum. The torch inductor is able, so I guess torch dynamo and torch inductor, essentially the torch compilation mechanism, is able to convert this to the following Pallas kernel. This is a simple reduction, and then we're able to generate the similar JNP sum version of this. If you look at a more complicated example, now let's look at RMS norm with reduction and element-wise operations. So for this RMS norm, in PyTorch, the way you'd write this is just the torch and then functional RMS norm, and then you would give the arguments, and then we would do the calculation for you. So when we lower this into a Pallas kernel, we actually end up emitting this Pallas kernel where you do the operations one by one, and you go through your sum reduction, you do your division, you do the reverse square root and the broadcast. Again, this is not the most performant way to write an RMS norm, but this is still a work in progress, and we're showing you an early preview of how we are starting with this most simplest form, and then we will optimize this by doing more reductions and fusions. So moving onwards, the Pallas backend is the first alternative backend we're introducing for Helion, and looking into the 2026, we're planning to work with more hardware vendors in order to improve Helion's ability to write the exact same kernel and be able to generate execute performant and portable kernels for different hardwares. With this, I will pass on to Jason to talk about mega-kernels.
Yeah, so another thing that we've been working on and improving is support for mega-kernels. So this is the idea that you take something that might originally be lots of different kernels, and you execute it with just one giant kernel that does lots of operations. And so Improving language, so there's lots of ways you could write mega-kernels in Helion today, just like you could do it in most kernel languages. There's different flavors of mega-kernels. So like there's places where you'd want to communicate data within a single SM, and for those we already have pretty good support for communication and synchronization within an SM. And
Sorry to interrupt, Jason. There is a question from the audience. The question is, there's many other DSLs out there today, such as Triton, that we lower to, QTSL, Gluon, Mojo, etc. What is the motivation for building another DSL?
Sure, yeah. So the big difference between Helion and other DSLs is the level of abstraction. So a lot of these other DSLs that have been coming out lately are lowering the level of abstraction. They're trying to go closer to the hardware and give people explicit control over low-level hardware details. And this comes with some trade-offs. So if you go lower level, you need to write more code, so your kernels become more verbose and harder to write. And you also give up on portability, where it becomes harder to write portable kernels because you basically specialized hardware information. And so there's some cases where that makes sense, where you want to use sort of a lower level language. But the goal of Helion is really to go higher level and have more portability. So Helion kernels should be easier to write, and so there'll be less code, and then also you can have hardware portability. And the way that we get hardware portability is through autotuning. So the Helion language has sort of a built-in autotuner, where you're basically defining a search space as part of the Helion kernel. And basically what you can view it as is we're taking a lot of the effort of optimizing a kernel and we're handing it off to the machines. So basically, rather than having a human spend a large amount of effort sort of specializing the kernel for every piece of hardware, you have a high-level semantics language that's the Helion language, and the autotuner extracts performance specifically for each hardware. So you can have one kernel that runs on all types of hardware.
Makes sense. There was a comment in the chat that your mic is a little bit difficult to hear. So if you can speak closer to the mic, that would be very helpful.
Okay. I just upped my volume, so hopefully that fixed it.
Okay, that's much better now. There is also another question here. Do you have any performance comparisons with handwritten Triton kernels?
Yes, we do. So the blog post and the slides from our PyTorch conference talk contain lots of performance comparisons.
Great.
All right. So getting back to mega-kernels, so we already have pretty good support for synchronization and communication within a single SM. One of the gaps there is doing cross-SM synchronization and communication. In Helion, you can have multiple top-level HL.tile loops, and this automatically gets mapped either into sort of a switch statement which decides what each SM will do, or it gets automatically turned into a persistent kernel. And this PR that I'm linking below, which hasn't landed yet, is adding support for HL.barrier, which allows you to do cooperative style kernels where you can basically do communication through memory with different tile loops. So in this example, you have a split reduction where you're basically doing the K accumulation in multiple SMs. You can then write partial results to main memory, and then you can call HL.barrier to ensure that all the writes to main memory from the previous loops have finished before you start the next loop. And this allows you to write a split K mapmul that's deterministic, so not using atomic adds, in a way that works in a single kernel. And with that, I'll hand it off.
There is another question from the audience. PyTorch blog shows that Helion performs better than Hetman Triton kernels. How can Helion perform better than Triton when Helion generates Triton?
Yeah, so this is a common question, and really the answer is better tuning. So if a human is writing a Triton kernel, they're typically going to try, a few different ways of implementing it, but they're unlikely to make very large changes to the kernel. They might spend most of the time tuning things like block sizes. While Helion, because it's a higher level language and uses an autotuner, is actually able to generate from a single Helion kernel thousands of different, often very different Triton kernels. And that auto-tuning process basically means that Helion is trying a superset of the search space that would be done by a human-authored Triton kernel. And it really demonstrates sort of the performance results about how consistently we're able to beat the performance of Triton, shows that tuning is really important. We're often the biggest difference about the performance of different kernels is how well tuned they are, how optimal they are, or how optimized they are. And what we see is that on one device, writing a kernel in Triton one way might be fast, while on another device, writing a kernel a different way might be fast. And the Helion autotuner is basically able to automate those rewrites through auto tuning to get better portability.
That makes sense. Yeah. Another question from the audience: could Helion be used as an alternative to inductor kernel templates? Would using Helion preclude fusions in this context?
Yeah, I think Helion could be used as an alternative to inductor templates. One thing we want to do is add better support for integration with inductor. So the basically able to add when you are calling a Helion kernel from a torch compile region, we want to be able to automatically fuse inductor ops into the Helion kernel. That isn't implemented yet, but Helion does already support some templating primitives, basically through closures in Python, which allows you to implement things like flex attention natively in Helion. And I think looking through the future, I think Helion's a great way to implement templatized operations.
Yes, probably one more thing to add there is that we'll talk about this more later on, but our plan going forward is also to have epilogue and prologue fusions in inductor, so that when you have when you torch compile a kernel that includes a Helion kernel in it, or when you use a Helion template inside inductor, we will be able to actually fuse the epilogue or the prologue of that kernel into your torch compile code as well. So we have some plans to have a better integration with torch compile to handle these fusions.
Makes sense. Another question from the audience. This is great. Is the Helion to Mosaic for GPU path intended to replace the current Helion to Triton for GPU? What is being used to do the Mosaic to device code compilation?
So I guess, okay, I'll take this one too. So for the GPU path, we don't intend on replacing the Triton version. We would like to provide, so for us, we have two different goals. One of them is to be able to port to different hardwares, and other one is to give the user the choice to try different things. When you want to generate code for a GPU, we don't want to limit you to our Triton backend. We want to, if in the future, when we build more backends, possibly for other GPUs, we don't want to limit you to using, okay, we only have the Triton, or we only have the Mosaic one. We want the user to be able to pick between different options. Let's say that we added, when we have the Mosaic backend, we will not force you to use one or the other. The one nice approach here is that you can either decide to choose a particular backend by specifying this in your config, or you can let the Helion autotuner decide, compare between the implementations for Mosaic, compare the compare the Triton implementation, and then see which one is faster. Perhaps Mosaic behaves better for certain code patterns. Perhaps Triton is better in other alternatives. So we would like to create the most flexibility for the user to either have the choice or to decide this via autotuning.
Another question: how is Helion's multi-GPU torch compile support?
Yeah, so Helion is a kernel authoring language. Sort of definitionally, kernels run on a single GPU, but you can in your kernel you can do cross GPU communication. So there's some examples in the Helion repo of distributed kernels, which are communicating across GPUs. For Torch compile support, Torch compile also supports multiple GPUs. You can call Helion kernels from Torch compile using multiple GPUs.
Great. Will, take it away for your section.
Yep, thank you.
Before we start, there is another question from the audience. Are there any plans to support ahead of time compilation in Helion, analogous to Torch AOT inductor?
Yes, so we already support this. So you can call on a Helion kernel. There's a function called you can basically explicitly compile given example inputs. We also support calling to Triton code, so you can actually just export a Helion kernel to Triton code, and then you can ahead of time compile that Triton code to PTX and just deploy that PTX directly. So there's a deployment guide on the Helion website that goes into some of this stuff.
Another question from the audience: how does Helion determine the search space of autotuning, and is that depending on the device?
Yes. So Helion for each device needs to understand the search space, and so there's lots of things like warp specialization, which are specific to one device. And in the Helion compiler, it's checking the capabilities of the device, and it's modifying the search space to tailor it to the specific device. And this sort of like adding additional search space items that are device specific is the main enablement work for adding new hardwares.
Great. I think we can move on to the next section here, Will.
Cool, sounds good. Yeah, so next I'm gonna talk about how to debug a Helion kernel and how to deploy a Helion kernel in production in general. So let's start with an example here, an iOS norm kernel. And once we have followed the algorithm and written the kernel, we might be thinking whether my algorithm is correct, whether it's producing the right numerics and stuff like that. So the first thing that I would do is to run the kernel with interpret mode to iterate, and we can insert like print statements, breakpoints within the kernel to print the intermediate results and observe the intermediate state to make sure the algorithm is correct. And as you can see below here, we can call it with the Helion interpret equals 1 environment variable, and then and run the kernel, and then we'll be able to see the print statements or use breakpoints as we want to. And then after a few iterations using interpret mode, make sure the algorithm is correct. You can move to the next step, which is to run the compile mode without auto-tuning, just to verify that the compile mode also works with the correct numerics. And here, if you run with auto-tune alpha equals none, it uses the default config, which is like which is a config that we kind of pre-computed and then should work for most of the cases. And then you can get the numerical output from it and compare to your reference and make sure the compile mode is also producing the correct numerical output. And then after you confirm compile mode kind of already works, so you can set the effort to quick to get some like quick auto-tuning result. And one thing you will notice is that in the log of the auto-tuner, you will see something that says one can hardcode the best config and skip auto-tuning with. That is the best config that the auto-tuner can find so far. You can either stop here and then just copy this config to your production setting, or you can also use the effort equals full option, which runs the auto-tuning for longer, and then usually might be able to find a better config for your kernel and input shape. So just to recap, to debug, you start with interpret mode, and then check the algorithm is correct, pass numerical check. And we in general want to make it so that whenever your kernel works with interpret mode, and it will also work with the compile mode. And then you can set the auto-tune effort level of any point from none to full to get to the best config for your kernel. Now let's recap a little bit on auto-tuning. So one Helion kernel can map to like many Triton kernel defined by a config. So, and then in Autotuner, we search over the entire config space to find out the best config given a time budget or like other computation budget. And usually auto-tuning should be done ahead of time, not just in time production, because in production, for example, in inference, the latency budget is very, very tight, and people should not be running auto-tuning in just in time in production. And they should instead just run auto-tuning ahead of time to get the best config, and then just hardcode that config in the production setting. So in terms of auto-tuning algorithms, today we have pattern search, which is a default, and we have differential evolution, we have finite search, and now we also have two open source contributions, the DE solo gate hybrid and also the LFBO pattern search. And in the future, we are also looking into LM guided search, reinforcement learning, and other techniques. Yeah, and sometimes user might also want to just search over some specific list of configs that they already have. And there is like a very simple way to do that as well. They can just pass it into the config list in the kernel setting, and the Autotuner would try each config for each unique shape and then pick the fastest from there. So now let's get into how to deploy a Helion kernel. So in general, once I have a Helion kernel and I know the logic is correct, there are two steps I should be doing to deploy Helion kernel. One is that use the Autotuner to find the best config for each input shape that I care about. Second step is to hardcode those configs in my production code. So let's get into step one first. So step one might look simple on the surface, but it's actually tricky when we get into a production setting where we have like multiple different shapes for a specific kernel. One thing we observe is that the best config for a specific shape X might not be the best for another shape Y, and also hard coding the shape into the kernel usually makes the kernel faster, but it won't work for another shape because it already hard coded for another shape. So the best approach is that you list out all the input shape variants that you care about, and then you find the best config for each one of them. So that might...
Sorry to interrupt, Will. There is a question from the audience here. Is the auto-tuning capability specific to a particular backend?
So I guess I can take this. So for auto-tuning, the algorithms themselves are not specific to backend. However, the configurations are specific, meaning that, like for example, we keep referring to warp specialization. It is not something that like it's supported on like an A100 Ampere series, for example, which means that if you need to use warp specialization, like warp specialization will not be allowed for that. However, this is not part of the algorithm. Like this is not part of the auto-tuner's responsibility. It is just like one of the metrics to optimize in the search space. So the auto-tuning algorithms can be used for any of the search spaces, but for each hardware, we limit the search space to that hardware-specific limitations or capabilities.
Makes sense. Another question from the audience. Do you plan to upstream the warp specialized Triton from Facebook experimental that's used in the Blackwell attention results?
Yes, we're planning to upstream that. We want to generalize it a bit more and make it work better for more kernels, but that's something we're hoping to do.
Another question from the audience. With full auto-tuning, can Helion using stock Triton reach FA3 performance on Hopper?
I think we already have, let me share the blog from this.
I think the blog results are on Blackwell, but I'd expect to get competitive with state-of-the-art performance on Hopper as well.
Okay, yeah, we'll publish more results.
One more question from the audience. Do you have a timeline to have these learning-based autotune search approaches?
I think for now, we are prioritizing, like we'll be talking about the work we are prioritizing for the next, the near future. For autotuning, we have some community contributions, and we're trying to see so in some cases they perform better than the ones we've written. So we're planning to promote some of those to the default autotuner. In the meantime, we appreciate, we would welcome any community contributions for these reinforced learning autotuning search algorithm approaches. So as Helion, we're developing everything in the open source, we would be happy to have any community contribution for anything we discussed today.
Yeah, and there's been a number of community contributions of auto-tuning algorithms that do use learning-based approaches. There's now 2 new auto-tuning algorithms that have already landed that you can select. They aren't on by default, but you can select them when you run the auto-tuner. And those basically are cost model driven approaches, where the idea is that rather than evaluating every candidate you consider, you have a cost model that tries to predict the performance of different candidates. And then based on that prediction, you filter the selection you actually try on the real hardware, basically used to accelerate performance things. So we've seen a bunch of improvements there, and the early results show that this actually outperform the non-cost model-based approaches. In the future, we're hoping to see as well reinforcement learning-based approaches and possibly like LLM-assisted approaches. I know there's been some experiments from various people in that direction, but I think new auto-tuning algorithms is a really interesting future direction.
Makes sense. Thanks for the answers. Back to you, Will.
Cool. Yeah. So we are just talking about how to deploy a Helion kernel, so when we look at production settings, usually we are not dealing with a specific input shape. We're dealing with various different input shapes to the same kernel, and for the maximum performance use case, if we want to have we should have each input shape variant to have its own fully specialized kernel, and in that case, we can set static shape equals true. That would hardcode all the shapes as static information into the kernel. But running in auto-tuning for all of those shapes could be prohibitive because that would just take too long. Or as a trade-off, we could have a somewhat generic kernel that only specialize on a specific dimension. If you want to do that, then you can add hl.specialize into the kernel definition, and then you can build up an if-else branch that creates the insightful input with the specific input size that you want, and then you run Autotuner to get the best config. And then you save the config for each scenario, and then in production you can just load it back using the same if-else branches. So shape specialization is very
Sorry to interrupt, Will. There is one more question from the audience here. May TVM or answer be applied to auto-tuning to find the best config?
Yeah, so TVM and answer are a completely different language. There isn't any interoperability between Helion and TVM or answer. Definitely, the design of the Helion language was inspired by Halide, which is TVM is based on, where you have a sort of semantics language, which is the main Helion language, and then a scheduling language which sort of defines the optimizations, which is analogous to the Helion configuration. Definitely there's ways where a lot of the ideas could be shared, but there's no way to call TVM or answer from Helion.
Back to you, Will.
Cool. Yeah. So we're just talking about shape specialization. As we have mentioned before, it's a very powerful way to fine-grain control what you want to specialize on and what you want to keep dynamic on. So currently we support static shapes equals true or false in the kernel setting. Static shape means equals true means we just hardcode all the shape information for all the inputs into the kernel that will only work for that input shape. Static shape equals false would mean that everything is dynamic, and then it will work for any kind of input shape. But because it does not hardcode the shape information, it might not be the most performant for all shape scenarios. And if you want to find somewhere in the middle, you can do hl.specialize on specific tensor shapes that will only specialize on that specific tensor dimension. In the future, we're adding more APIs to make it more flexible on how to specialize on different shapes or strides. For example, specialize on shapes outside of the kernel definition, specialize on tensor stride, and also have settings to avoid the 0-1 specialization that we inherit from the fx trace. So that the kernel from the m equals 1 shape can still be used for the m larger than 1 shapes. So let's go to step 2, which is like we already have all these configs, and then what are the common ways to hardcode these configs in my production setting? So if you only have a specific one configuration you want to deploy, you can just add it as a decorator onto the Helion kernel function and with other config information. Or if you have a few configs and you want to dispatch it based on the number of elements in the tensor, you can do something like this to build a custom router. Or this is another pattern that we see in our users. You can, if you want to have more fine-grained control on how to dispatch, you can build like a if-else branch with many branches, and then within each branch you have the best config hard-coded, and then at the end you return a hidden kernel with the best config chosen based on the input shapes. We are also looking into discussing specific issues, proposals from users on how to make this deployment for variant shapes easier in the future, as we expect this to be a very common use case.
Great, thank you, Will. There is a question from the audience here. Do we select the best config solely based on the kernel performance, or do we also consider kernel compilation time? Additionally, is it possible to support user-defined selection criteria?
So, okay, I can take this one too. So currently our cost function for descending is entirely based on the kernel performance. But it is theoretically possible that like we could expose more APIs for user-defined cost functions. It's also possible that like we could expose an API so that you can do like a weighted sum between compile time or like the kernel performance or some other criteria that we might want to include there. Like if this isn't something that interests you, please create a GitHub issue and then explain like how you would like to use this function. These are currently we don't support it, but this is something we could theoretically support.
Yeah, one thing I will add is we do have a timeout, and so if a configuration takes a really long time to compile, we actually just kill the compilation and exclude that config from the search space. And so if you're looking for a configuration that say takes less than 30 seconds to compile, you can set the compile timeout to 30 seconds, and then we'll just discard all configs that take longer than that to compile. You can also customize the cost function by subclassing the autotuners. So like all of our autotuner classes have basically an evaluation method. And if you create a subclass of the autotuner and you sub in your own evaluation method, it should be pretty easy to have sort of like weighted averages or different sort of metrics to optimize.
Yeah, one thing we've discovered while working on Helion is that Helion ended up being the greatest Triton fuzzer ever created. We're able to create Triton kernels that are not meant to be created in some sense. So this way we're seeing some really high compilation times. So we're working with the Triton teams in order to improve these kernels as well.
All right, so I can talk about what we have planned for 2026. So on the technical front, some of the things that we have planned are adding distributed support in Helion. There was a question around this earlier, and Jason mentioned that we're adding operations to be able to communicate with other kernels that are running on the GPUs. We'll extend the support for that. We will also work on automatically generating backward kernels from the user defined for kernel in Helion, as well as also supporting prolog and epilogue fusions, which also Jason briefly mentioned from an earlier question. On community engagement, we have an upcoming Helion tutorial that we'll be hosting at PLDI conference. This is being held in June 2026, so please stay tuned for that. And we're also working on other events that we will let the community know as those are finalized. Going on to the next slide. Actually, there is a question from the audience. You talked about Triton and Mosaic backends. Are there plans for other lower level backends like TLX, Gluon, or QTSL?
Yep. So I know that there's some interest in other backends as well. There's some people who are exploring alternate backends already, and we're definitely be open to conversations about additional backends and community contributions there.
All right. Going back to the slide. Actually, one more question from the audience. What is the boundary between Helion and torch inductor? What optimizations are done in Helion versus in inductor?
Okay, maybe I can take this. I think I touched upon this a little bit earlier in the presentation. Essentially, the way Helion uses torch inductor is to only consume the A10 to Triton code generation part of torch inductor. Aside from that, Helion is an entirely standalone process where we do our own IR generation, we do our own optimization passes. Traditionally, torch inductor has scheduling and other FX passes that do optimizations, or fusion passes, etc. But Helion doesn't actually use these because Helion has its own lowering passes. We try to make sure everything is based on the configurations that the user has defined. So we try to not automate torch inductor's optimizations.
Makes sense. Next
I think this
slide,
is the last slide, James.
There is one after this, right, Will?
Oh, sorry.
Will, do you have screen control, or who has screen control here? Can we go to the next slide? Okay. So yeah, this is the last slide. So we encourage everyone to try Helion today. Everything is open source. As we mentioned, we would love for more community contributions to Helion. And you can connect with us directly on the GPU Mode Discord in the Helion channel. We're there every day answering questions. So feel free to drop in there and communicate with us. There's a number of links here on the slide. There is a link to the PTC talk that Jason gave on Helion. This is for the beta launch, and this also has various performance benchmarking we had done at the time, including on the attention kernels. So feel free to check that out. If you search on YouTube, Helion PTC, you'll be able to find this. The code is on GitHub, PyTorch Helion. We also have a documentation website at helionland.com. And we also have a blog that we publish for the PTC launch at PyTorch.org blog Helion. Any other questions from the audience? Right, there's a question. I think Woz had mentioned this. This is, I think, yeah, what optimizations are done in Helion versus inductor? We already answered that. During Helion autotuning, I've seen some Triton compilation errors. Why does that happen? This is what Woz was talking about the fuzzer. Yeah, do you want to elaborate on this again, Woz?
Sure. So Triton was designed for writing kernels by hand. And as far as I know, Torch Inductor was the first system that actually started emitting Triton kernels. So with Helion, we actually took it to the next level where we're auto-tuning over a large search space, and we're when you look at like the Triton auto-tuning, you're generally auto-tuning over hyperparameters. But in Helion, since we have access to the entire kernel, what we can instead do is to generate different kernels for different auto-tuning parameters. An example to this would be for indexing, we can use pointers, we can use tensor descriptors, we can use block pointers, or we can do other reduction operations as well. So what this means is that Helion is able to generate so many different variants of Triton kernels that not all these kernels are supported by Triton language by default. So what we've been doing is, as we discover these unsupported kernels, we create reproductions, and then we share these with the Triton teams, and in order to better improve the Triton's front end, so that we can support these kernels. In some cases, we also generate kernels that are just too large or not feasible. So we try to write heuristics so we can avoid these impossible kernels. But yeah, as I mentioned, like Helion turned out to be the greatest Triton fuzzer created. So we're able to we're experiencing these issues and then we try to create reproductions and resolve them.
All right, I think we can take a few more questions since we're close to the end of the time. I see one question here. Following up on that last point, is the right way to think of the inductor-Helion relationship is that Helion is leveraging the inductor-Triton backend?
Yes.
Yeah, so inductor contains a lot of graph level optimizations, but because Helion's just a single kernel, there's the sort of graph is just size one. The graph optimizations in inductor don't apply. But basically Helion hooks directly into sort of the code gen backend, and is really, the thing that inductor's providing is the mapping from the thousands of PyTorch operators to Triton code, which allows basically regular PyTorch operations to be used in the Helion language.
Yeah. One thing to call out here is that like with Helion, we have the guarantee that a single Helion kernel will be converted to a single Triton kernel right now, meaning that we do not have any breaks in this kernel. So we have limitations on, I guess, like what kind of optimizations we can do based on that.
Yeah, I also add some color, which is that in inductor, using torch compile inductor, like using torch compile path, it's like automatically discovering fusion opportunities. But here, user is telling us what operations they want to fuse together, and Helion just generates the single Triton kernel for that list of operations combined.
All right, I think we can take this last question. What's the best way for someone new to contribute to Helion?
Yeah, so open a pull request is basically the idea. If you're looking for ideas of stuff to work on, or looking for help, you can look at our issues on GitHub, or you can join the GPU Mode Discord channel and ask us some questions directly there. I think there's also one question you might have missed about MLAR. So Helion itself doesn't use MLAR, but Triton is based on MLAR.
All right. If there are no more questions, I think we can end the webinar here today. Thank you, everyone, for attending the webinar, listening to our presentations, and appreciate all the questions. I think this was very fun, and we should definitely do this again. As we mentioned, we would welcome any OSS contributions from the community. Everything is open source on our GitHub. Please check out our documentation and PyTorch blog and the talks that are on YouTube. There should be multiple talks that Jason gave on YouTube on Helion. So if you want to catch up on different kind of software architectures and performance benchmarking, you should be able to learn all of the details there. And do connect with us on the GPU Mode Discord on the Helion channel. Thank you very much.
Okay, thank you.
You know,